We start the lecture by giving the overview of optimization in engineering and machine learning. In this class, we list the outline of the topic included in this lecture. So we're going to start with giving the overview, the general setting of optimization in terms of mathematical setting. And in order to study and go over all the all the contents, there's going to be some terminology, some keyword and computational consideration that you need to know. Okay. And in this lecture, we describe briefly about all the optimization problem types. Those are unconstrained problems, constrained problem, LP, QP, linear and quadratic programming. Throughout the semester, we will also give you applications of optimization, focusing on machine learning problems. We give regularization techniques that are very common to use right now in regression problem. And I think after the midterm, we will discuss about one of the essential tools, which is duality theory, especially when we talk about convex problem. These will play important roles in order to discuss about problem properties. When we talk about unconstrained optimization problem, we give you just a brief concept of things you learned before, probably from from the other class of optimization, gradient descent. But we will go over to the extension that is used right now in training deep learning model. Those algorithms are momentum accelerated gradient descent. These becomes option in library command as optimizer. For example, imsprop, imsprop, Adam, okay, those things. We will go over its mathematical principle, and unlike traditional optimization approach that is trained by offline or batch optimization, you see that recently in machine learning, people implement mini batch optimization, okay, where you split the training data into mini batch. So we will go over the concept. Why do you need to perform mini batch, and what is its properties? When we by the end of the semester, I hope that we will have time to talk about approximate method. These are algorithms that are beneficial for large-scale computing. And of course, for each algorithm, we only have time to discuss about fundamental properties. For example, convergence, or its accuracy after a finite number of iterations. So in this class, I would say that we focus on formulation, mathematical properties, but probably we wouldn't have time to go over the proof of convergence. Okay. In order to learn this class, I hope that we have background in linear algebra. A lot of matrices here. So these keywords can be checked out before. If you don't know vector matrix norms, please review. There's going to be many kinds of matrices, especially symmetric matrix, positive definite matrix. These will be discussed a lot, especially when we talk about quadratic programming, eigenvalue, eigenvector of matrices. All right. Please review. Some of the fundamentals in calculus also required, all right, especially at the beginning of the first few lectures. I hope everyone is familiar with the term, of course, derivatives, right? But then the topic you learn from calculus will be extended to multivariate calculus, calculus of several variables, all right? So when you have a function, of several variables, derivative is extended to the concept of gradient, right, or the Jacobian. Okay. The second derivative, okay, second derivative is called Hessian matrix. So I hope that you review. All right. There's going to be the times that we wouldn't spend time on taking the derivative of some known functions, and if you haven't seen this before, I hope that everyone has seen it, because this is in undergrad class. But please review, because so most of the time I find that a student almost forgot how to compute gradient and Hessian matrix. All right, when we talk about algorithm convergence, these are the times that you need to understand the concept of sequence and convergence of real numbers. Okay. So I hope that you spend maybe 1 or 2 weeks on reviewing this, and I have some of the video lectures as well, especially in the linear algebra, so you can check out on my website. Okay, we're gonna start by giving the mathematical setting of optimization problem. Okay, optimization problem is the following. All right, we have a function f0 or f0. Okay, this is called objective function. All the functions involved here in the general setting are function of several variables. This is a function of a vector Rn, but mapped to a real number. So this is called scalar valued function. Scalar value function. For example, this is the if I write in this form, x1 squared plus 2x2 square, right? So this f0 maps from R2 to real number. Okay, it's a function of R2. It's a function of vector in R2 because it's contained two variables. Okay. Fi here, this is called inequality constraints function. In the problem setting, it says that we aim to minimize the objective function f0, where we have the constraint that the value of x that you're going to find need to satisfy that all the fi must be less than 0. And there are many i's here. There are many functions, many inequality constraint functions. Plus, there are equality constraint functions. All right, this is called quality constraint, inequality constraints. Okay. Okay. For example, if you aim to minimize x1 squared plus 2x2 squared subject to x1 plus 3x2 less than 0, and probably you have this. Okay. So this is a setting of an optimization problem. The objective function is this quadratic in x. Inequality constraint function is linear, x1 plus 3x2 less than 0. The last one, sine of x2 equals 6. This is equality constraints. Okay. How many constraints do we have, Napat, totally?
2 constraints.
2 constraints. All right. 1 equality constraint, 1 inequality constraint. Okay. All right. In this setting, now we're going to represent the constraint function in terms of set. We define the constraint set C is a set of x. All right. You're collecting the member x, the vector x, such that it satisfies all inequality and equality constraints. Okay, for example, if my constraint, if my inequality constraint is x1 plus x2 less than 2, all right, and I have x1 square plus x2 square equals 4. My constraint set is, of course, so I'm gonna draw, right? I'm gonna look how it looks like on the R2 plane, x1 and x2 here. The first constraint, how can you describe this? Bhumipat, x1 plus x2 less than 2. How can I describe all those vector x that satisfy this inequality? Who is Bhumipat? So I'm gonna draw a line, right? This looks like a line, right? Where's the slope, Bhumipat? X. So basically, you think about, in order to first this inequality, but you know that this inequality is associated with this equation, right? x1 plus x2 equals 2. So it's a line with the slope of slope เป็นเท่าไหร่ Bhumipat?
-1
So slope, the slope is -1, right? And the y-intercept isจุดตัดแกน y 2. Okay, right? All right, but all those x that satisfy the yellow area, the inequality constraint function, what are those area, Panithan? Is it below or upper the line?
It's below this.
Below, right? Below. All right. But then the constraint set is all those x that satisfy both inequality and equality constraint. So you have intersection here. The comma in mathematical sense, it means that intersection. Everyone understand? Agree? Like if you say that, oh, all those x that makes this guy less than 0, if you have comma, it means that it has to satisfy everything, like with the keyword and, with the and operation. Okay, now, how does it look like, this equality constraint? Napat?
It is a circle with radius of 2.
It's a circle with radius of 2, right? Okay. And then, but the area of this equality constraint, where is it? Where are the areas, where are the region of those x that satisfy this equality constraint, Napat? Is it on the circle? Is it inside the circle? Outside the circle?
On the circle.
On the circle. So basically, the constraint set at the end with this example, the set C is What do we do with these two areas? As I mentioned, that you have to do the intersection, right?
Yes.
So it's the intersection of the line, the circle, and the yellow area, and the result is Titipong.
It's the part of the circle which are below the line.
It's the part of the circle that below the line. Yeah. So that's the thing, right? Because we it's going to be better if everyone can join in. Does it include this point, Titipong?
Yes.
What about this part? Does it include?
No, it doesn't.
No. Right? So it's the intersection between the circle and the yellow area. Okay. Is it clear? So this is your constraint set C. Okay. Next. So by now, this I'm giving a lot of definitions here. So by the end of this slide, when I talk about objective function, you know what it means, right? Constraint functions, constraint set. Last, domain of the problem. Okay, the domain of the problem is a set. It's a set of basically the domain of all the functions involved: objective function, inequality constraint function, and equality constraint function. Each function can have implicit, explicit or implicit domain. It depends, and you're gonna collect all those domains and perform intersections. For example, the cost objective of Napat, if you perform a classification in machine learning and you use neural network, what is the cost objective? Can you recall?
Cross entropy loss.
Yes, what is it?
Yi log y.
Yi log
Yi hat.
Yi hat. So I'm gonna use the variable x here so that we know that this x is actually a parameter of a neural network, right? It's an optimization variable. Is it all, Lapat? Binary, maybe binary classification. Oh, it's this, right?
Yes, log
1
minus yi hat.
Okay. So for everyone that probably not haven't seen it before, it basically these y are measurements, are the labels in classification problem. The variable x here, optimization variable, this is actually parameter of neural network. Yi hat here is actually the output of your neural network, okay, in terms of probability. Don't worry about that, but because the point here, I want to mention that this is your objective function, right? In this binary classification problem, is unconstrained. There is no constraint functions. But if you take a look closely, you see the function log here. What do we know about the log function? Does it have a domain, implicit domain? I mean, we're in the world of real number, all right? You aim to find x that belong to a vector in Rn. It's not in the complex plane. What I'm saying is just this. So the concept of function log of real number, right? The domain is this argument has to be Panithan. Panithan. Log has a domain, right? Log of -1, -10, of course, is not in our interest because these return complex number. So when we restrict ourselves to real vector, the log function has implicit domain that only takes a positive argument. In this example, what I'm trying to say is the domain of your objective function is a vector R. So sorry, non-negative, positive vector R. Okay. I should I use notation. It's probably I write it again. Rn Euclidean space is as a vector. If I put one plus sign, it means that it's non-negative, right? If I have two plus signs, it means this has to be positive. Right? So the function log has implicit domain. In this example, the domain of the problem is Rn++. Okay. Now let's okay. Once a mathematical optimization problem is given, all right, and as you see, the goal is to minimize. You want to find, but basically, first of all, when you define, when you have characterized the constraint set by looking at the inequality and equality constraint, you see how the constraint set look like, right? And you see all the members in there. Any x that belong to this set C satisfy the constraints, but you're gonna pick one. You're gonna pick one that your sorry, this is your objective function. You're gonna pick one that has minimum objective value. Okay, so this is a goal of optimization. Optimal value. Okay, optimal value is then defined as the infimum of objective value function, where you take the infimum over the constraint set. Okay, does it make sense? I put a simple message for you to read what the infimum means. Has anybody look at that? The infimum of a set is actually the greatest lower bound of a set. It's basically like a minimum, but there's a little distinction. For example, I can also, if you take a look at the positive real axis, the positive real axis, 0 to infinity. Okay. The lower bound of this set is any number that is less than 0. Okay. But the greatest lower bound of this set is the greatest lower bound ที่ใหญ่ที่สุด. Okay, is 0. So the infimum of positive real axis is 0. Okay. There's going to be a slight difference between infimum and minimum. If you talk about on the minimum of a set, okay, everyone know that the minimum of a set is actually the value of a member in the set that has the minimum value. The distinction is that the minimum of a set must return the member of that set itself. For example, so there's going to be a difference here. On the positive real axis, 0 is not the minimum of this set because 0 doesn't belong to this set. Okay. All these things can be studied in real analysis. Okay, you can read further on that. Okay, optimal value is defined as the infimum of objective value function. There are some terms here that I'm going to explain. We say that a point x that belong to the domain of the objective function and the x that satisfy constraint set, we say that x is feasible. Okay, a feasible point means that x can be candidate to compare with the objective values. Let me write again. Suppose this is your objective function. Suppose your constraint belong to this set. All right. So all these set here, all these members here are feasible. Okay. We say the problem is infeasible. Okay, if you cannot find any x at all in the constraint set. The constraint set is empty set. And we have defined that when the problem is infeasible, we assign the value of the of p star, the optimal value, to infinity. Okay, so by now we're gonna refer to this term a lot, p star. All right. If the problem is unbounded below, for example, a simple example, if f not x is x objective value is a straight line function, and you state the problem as, oh, minimize x where x can be any real number, right? You see that this is a problem where, oh, I can choose x to be as small as I can, arbitrarily small, right? In this example, the problem is called unbounded below, because you can choose x to be small and p star tends to negative infinity. Okay, in optimization, all these things are important because this is a property of optimization problem. And the way you formulate the problem from application will end up with this property. I would say if the problem is unbounded below, the problem is not interesting to solve, right? So in practice, if you're the one who formulate the problem yourself from your research, from your, I don't know, from your problem of interest, if the problem end up with having the property of unbounded below, you need to go back to reformulation process. All right. Next, as I said, that a feasible x is any x that, okay, that is fine, it satisfies the constraint, it belongs to the domain. Now, if you compare, all right, you get bunch of candidates here. For one x, you compute. So suppose this is x1, you compute the objective value. For x2, you compute its objective value again. And now you're gonna compare, right? Compare this guy and pick the minimum one. And that's how you get P star. All right. The candidate that is objective value equal to P star is called optimal. All right, it's called optimal. The term locally optimal is the following. Is in the sense that this x, all right, if you minimize the same objective value function and you and you look for other candidates in the neighborhood of x, all right, those vectors z are all the vectors that lie closely to x. How close? Determined by epsilon. Maybe I need to refer a little bit. When you see this notation, this is 2 norm, right? These give you the distance between vector x and vector z. Suppose vector x is here, right? So all the vectors z that lie closely to x by the radius of epsilon is actually all the vector inside the circle, right, with the radius epsilon. This is how you look on the R2 plane. Okay, come back to this definition. So it says that if you look for any candidates in the constraint set and those vector z lies in the neighborhood of x, x is called locally optimal. All right, if you have solved this one. If I explain in the not this one, sorry. Okay, maybe this one. This is your f0x. Okay. This x is called locally optimal because if you have solved the same problem with the same objective, but now you have this additional constraint. You don't look for the entire plane. You look for all those z that lies closely to x. Okay, in this yellow area. All right. If you have solved this problem, okay, it returns the solution x. Right? You look at this. You don't look the entire plane, as I said. You look for candidates in this area. It returns the vector x as an optimal point. So this x is called locally optimal. There can be many locally optimal points. These as well. This x is also locally optimal. Now to I would say, well, all we have seen, these are terminology in optimization. Now we're gonna review again if you understand all these terms correctly. We do it together. So here I give a list of problems. Let me clarify. For the first one, what I mean is that, okay, we minimize 1 over x. I missed one point. X on the positive real axis is on the non-negative, on the right half plane, basically. Okay, if I state the problem, optimization problem like this. So let me sketch. So in order to explain mathematical property of this problem, probably we sketch the graph, okay, and kind of inspect the solution by the knowledge we know before in the calculus. So 1 over x, the graph looks like this, right? Right. So you're going to find all these x on the right half plane. I mean, on the real axis. You see that the infimum of 1 over x, right? The infimum of the function 1 over x, where x is positive, where x is non-negative. The infimum is it clear that the infimum is 0?
Yes.
Okay. The infimum is 0, right? But then, because when x is really, really huge, 1 over x is 0. But then, can you obtain that point? Can you obtain that x that makes 1 over x 0?
No.
That point is not attained because you need to extend x to infinity. All right. So in this problem, p star is 0, optimal value is 0, but there is no optimal point. All right. Go back to the definition of optimal point again. X is optimal if when you evaluate x in the objective value function, it has to be equal to p star. Next, the second one, negative log x. How does it look like? Thitipong.
It's occur from
Okay.
like
This is log x, right?
yes. And
So the negative log x would be the other way around. Flip around x axis, right? Okay. Now, what's the domain of the problem? Go back, domain. Domain of the problem is actually domain of all the functions involved, objective, constraint, and all those domain you perform the intersection. So in this one there is no constraint functions, right? Domain of the problem is actually the domain of what? Of the objective function, which is
Positive real number.
Yes. Okay. Then again, this problem, you see that, in order to minimize the negative log, the problem is unbounded below. P star is negative infinity. Okay. Right. Problem 3, should I? So the calculation involved will be left as an exercise. Again, this is a simple version of the cross entropy function. Okay, x log x. X log x, if you, again, the domain will also involve, because you have x times log x. So basically x has to be positive, right? So this graph, this function look like this. Okay. Yes, you can use the basic calculus. If you take the derivative of x, right, set it to 0, solve this one, you're gonna see that this point is 1 over e, and the p star is negative 1 over e. So please check as a simple exercise. All right. So we say 1 over e here is optimal, because if you plug this in f of 1 over e, you get p star negative 1 over e. Now I'm going to jump to number 5. All right, number 5. Number 5 is a cubic function, x cubed minus 3x. What does it look like? I use computer to plot. Should I? Okay, let's see. Probably it's not accurate, but you can use computer to plot and see. Okay, if you minimize this function, okay, on the real axis over all the real number, you see that p star, the optimal value is, it's again unbounded below. P star is negative infinity, but there is a local optimum when x equals 1. How can I find this x? Can you review how to confirm that this is true? ภูมิพัฒน์ภูมิพัฒน์
ครับดิฟกับดิฟสมการ
Yes, we take the derivative, right? And what? You take the derivative and set it to 0.
To 0, yeah.
Right? And then how do you verify that it's a local optimum? Because in the calculus, remember that we have both. You remember the point where you set the gradient to 0 is called, what do we call? All those x that satisfy 0 derivative. Critical. Stationary point. Yes. Stationary point are not necessarily local optimal point, right? On this graph, okay, both, on the blue, the blue term here, the blue, these are stationary point, but the green one is local optimal point, because you need to check what the second derivative, right? The second derivative. So if the second derivative is positive, it is a local optimum. If it's negative, it is a local maximum. Okay, this is from calculus. Now, okay, so probably problem 6. Okay, if I sketch, now it is extended to a function of several variable. It maps from R2 to R. So now it's gonna be like a surface if you draw it on the R2 plane. But if you just look at the objective value function, that is quadratic, right, in x1 and x2. So if you see this, what is the choice of x1 and x2 as a vector in R2? That makes this guy minimum. What is the choice? So I think we can all inspect that. Because this is a sum of non-negative term, right? Of course, we can make both terms 0 by choosing x as 2, 2. Clear, right? I mean, this is a sum of non-negative. The objective cannot be negative. Okay, so in this case, we say, of course, we conclude that P star optimal value is 0 and x22 is optimal. Easy. Now take a look at problem 7, 8, 7, 8, 9. For 7, the same objective value, but now we have constraint set. Suppose this is inequality or equality constraint. Equality constraint. Now I'm going to sketch equality constraint set on R2 plane. Because I mean our optimization variable is a vector in R2. And again, as you see, this is the line, right? So the constraint set is actually all the members on this line, right? Because this is constraint, this is equality constraint. Okay, now if you minimize this guy, you have to imagine like there's a bowl. I'm not sure if you can kind of visualize this. The area you see right now, this is kind of this is going to be your constraint set, right, on this line. The function value will grow as a surface. Okay. But and then okay, can you see that I'm going to leave you verify that now this is you cannot freely choose 2, 2 as optimal because 2, 2 is here, right? 2, 2 is here. It's not on the constraint set. You have to pick only on the you have to pick like the candidates on this blue line. All right, and verify that, if I pick this one, pick this one, pick this one, when I plug this in, okay, which point give me a minimum? But of course we don't do that, right? There are a bunch of infinitely many numbers on this line. Okay, now we can just be very heuristic because the way we can look at this as without learning like all the techniques in this class, because I mean you just for this problem you can see that even though I have two variables, even though I have x1 and x2, because they are related by equation, this equality constraint, what if I can get rid of one variable? What if I can just, I can say x2 is 2 minus x1, right? I can get rid of the constraint, but now I write x2 as a function of x1, and I plug it back here. Okay? Now it's going to be a function of x1 only. Okay? 2 minus x1 minus 2, right? It's a function of x1 only. Now you get rid of constraint function and it becomes unconstrained function in terms of x1. And now you can solve it, right? Okay, so please verify that p star is 2 and x equals 1, 1 is optimal. This is one of the techniques we will see too. This is called constraint elimination method. Okay. Next, 16. What about the problem 8? Okay, the only distinction is the constraint set. So it's on. Is it the same? The constraint set is the same. How does it change, Napat? How's the difference between 8 and 7?
The y-intercept.
The y-intercept now with the y-intercept now is now maybe I change to the green one, right? This is problem 8. So in this problem, you would see that this constraint set actually passed the 2 point, right? It's actually the point where the objective value is minimum over all the arbitrary choice. So P star can be made to 0 and 2 is optimal. Last one for this section, number 9. Number 9, what we have is, first, how many constraints do we have? Pong.
Two
constraints.
Equality.
Yes, 2 inequality constraints. Now we're going to sketch the constraint set. First one, how does it look like on the plane? Jitipong.
It's a parabola curve.
Parabola. This or this? First or second one?
The second one. The first one.
The first one, okay. This is the on the line. This is this equation, but this is when you have inequality constraint, like you have inequality sign. So what is the region corresponding to this one, Jitipong?
Under the parabola. Napat, what do you think? Yes, of course, I understand that it can be confusing, but these things can be checked.
It's the region above and
above or under the parabola. Napat think is above.
Above and include the line.
But Titipong think is under. How can we check? Panithan, if we are not sure, how can we check?
We can
I think I learned it in primary school.
Substitute some point in that region.
Yes. You just pick some point, right? Like maybe this is the point of 0, 1, right? And see if the point satisfy. Titipong, blue or yellow?
The blue one.
The blue one. Okay. This is the region where it satisfies the first inequality constraint. What about the second one? How does it look like on the plane? Pumipat.
It's in a circle with radius of square root 2.
Okay, it's a radius. Sorry, it's a circle with the radius of square root 2. All right. Okay. Region. What are the region? What is the region? Inside the circle. Right, inside the circle. So the constraint set is you have to intersect the blue and the pink areas, right? Go back. See, the constraint is a set of all the point x that satisfy both like all of them. In terms of set, you need to intersect. So it's going to be, I'm going to paint again with what? With the, maybe with this color. Right, you perform the intersection. Right? Maybe it's not clear. So I'm gonna basically delete the whole thing. Just and leave that. Okay, this is the constraint set. Is it clear now? All right. Now we look at we're not done yet. Okay, what we have seen is just to characterize the constraint set of this optimization problem. What we do is we minimize the function x1. How can we do this? The objective is only reflects the value of x1, right? x1 equals 10, x1 equals 5, all right? But you can only choose the vector x in the pink area, right? If you pick this point, the x1 corresponds to some number, right? The thing is you want to minimize x1. So what do you do? Now, Pat. If you pick any x in here, it reflects in the same objective value, right? What I'm drawing is what's so-called the level set that I'm going to explain next in the couple slides. But just by looking at the problem, this problem now, you can see that if I pick any point along this line, again, it achieves the same objective value. But which one in the candidate, in the constraint set that should give me the minimum objective value, the minimum x1?
ตรง intersection ระหว่างเส้นฟ้ากับเขียวครับทางซ้าย
Yes, you look at the point that is furthest left on the constraint set, right? Because you see here that these points give me the minimum x1. So when I read that, I know that x1 star is -1. And then I just look at the equation, right? And I can see that, oh, x2, at that point, x2 star is 1. I put it back. I put it back to the constraint, to the objective function. So, and that, of course, p star is -1. All right. For problem 10, we don't have time, but I hope you verify. The point of problem 10 is that please verify that optimal point is not necessarily unique. Okay, that's another keyword. What does it mean, unique? Unique ก็คือเป็นไปได้แค่จุดเดียว optimal point หมายถึงปัญหา optimization อาจจะมี optimal points หลายจุดที่ achieve the set ที่ achieve optimal value ค่าเดียวกันไปลองคิดดูนะไปลอง sketch ดู Okay, this is some basic terminology of optimization problem. I think we stop here, and in the next lecture we talk about examples and again some more terms that involve sublevel set, contour, gradient, all these kind of things.